All right, our last example in section 3.5 is number 33, and here we're asked to find y double prime, so the second derivative of y, with respect to x, and it tells us by implicit differentiation. This may be a case where we could solve for y explicitly in terms of x, but it's probably actually easier to just use implicit differentiation. And because I've been using the dy dx notation throughout this handout, I'll go ahead and use the prime notation just for a little change of pace. So again, implicit differentiation, my general method is that I have to find the derivative of both sides. So here the derivative of x cubed is 3x squared. The derivative of y cubed, I'm bringing my power down. I think of y as a base function. I rewrite my base function, I raise it to one lower power, and then I multiply by the derivative of that base function, and the derivative of y I'm writing as y prime, and then the derivative of 1 on the right hand side is 0. Now before I can find y double prime, I need to have this solved for y prime. So I'm going to take the 3x squared and subtract it over to the right hand side. And then I'm going to divide both sides by 3y squared to get y prime by itself. And here, as we've seen in other examples where you have to find a second derivative, it's probably in your best interest to go ahead and simplify as much as possible. Now, FYI, we can write this as negative x squared over y squared, or we could write it as negative x squared times y to the negative 2. 6 of one, 28 of another, doesn't really matter. So now I'm ready to find y double prime, which requires, if I'm using, which I will use, this middle version, that requires the quotient rule. If you separately for yourself want to use the product rule on the last version, the negative x squared times y to the negative 2, I encourage you to do that and then see if our answers match up at the end. All right, but I'm going to go ahead and use the quotient rule. So the second derivative, y double prime, the derivative of the first derivative, that is denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now remember, the derivative of y squared is 2y times, whoops, let me keep using my prime notation, times y prime. Okay, so that is denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, and then I'm going to simplify a little bit so I can try to see what I've got here. So I have negative 2xy squared plus 2x squared y times y prime all over y to the fourth. Now, what I next have to do is actually substitute for the y prime. Okay, in other words, my answer to y double prime should not have any derivatives in it. So I'm going to substitute for y prime what I know that's equal to negative x squared over y squared. So y double prime is now negative 2xy squared plus 2x squared y times negative x squared over y squared, that's y prime, all over y to the fourth. So let me see what kind of simplifying I can do with this. Whoops. So I have negative 2xy squared. Now on this second term, I have an x squared times a negative x squared, and then I have a y that can cancel with one of the y's in the denominator, so that I have negative 2 times x to the fourth over y. Make sure that I'm not forgetting anything. All over y to the fourth, so it's okay to take a moment, step back, and give that another look. Now, what should I be doing to simplify further? Well, one thing is, maybe it would be nice if I got a common denominator in the numerator. of y. So if I rewrite that first term as 2xy cubed over y, then I'll be able to combine my two numerator terms. So this is all algebra that we're doing here. Just make sure that if I were to re-simplify that first term in the numerator, it would in fact be negative 2xy squared, which is equivalent to what I have written here. Now I've got a common denominator in the terms in the numerator, so I can rewrite that as negative 2xy cubed minus 2x to the fourth all over y, all divided by y to the fourth. And what that means is that in fact, well, I can look at this a couple different ways. Dividing by y to the fourth is the same as multiplying by 1 over y to the fourth. Or I can think of the y in the numerator as coming down to combine with the y in the denominator to make a y to the fifth. Let's see, then I could factor a 2x out of the numerator, and you might be wondering, like, why are we going to all this trouble? But I think you'll see in a minute, and I think you'll be pleased. We have negative y cubed. Actually, why don't I pull a negative 2x? Since both of my terms in the numerator are negative, I'll pull a negative 2x out, and that will leave me with y cubed from the first term and x cubed in the second term. By the way, how nice is this? I have a y cubed plus x cubed term here in the numerator, and I was told that x cubed plus y cubed, or y cubed plus x cubed, equals 1. So in fact, what I have is negative 2x times 1 all over y to the fifth. So ultimately, my y double prime actually simplifies to negative 2x over y to the fifth. Well, that's kind of cool, right? So again, you might be asking yourself, gee, do we have to do all that simplifying? Well, not necessarily. In this case, you would have needed to simplify the y prime to make it easier to find the y double prime. And when you found the y double prime, it would be important to substitute for the y prime its equivalent, as we did in the first line there of the y double prime at the end. That is all important. The rest of the simplification, well, maybe not super important. It would be great if you could understand enough algebra to be able to do that. And supposing then you were asked to find y triple prime. Well, obviously, finding the third derivative with this much simplified second derivative would be tons easier than if we had the much more complicated y double prime that we had originally. So I don't really know what to say about simplification. I wish you all could do a good job with it, but we do what we can.